Mathematical functions are curves in continuous motion. When plotted, a complex polynomial flows across the plane, shifting its direction repeatedly as its values change. We can identify the coordinate where a function changes direction, the turning point. To qualify, the curve must shift from rising to falling, or conversely, shift from a falling trajectory back to a rising one. When graphing complex equations, we cannot rely on plotting individual points to find these twists. We need a way to predict the curve's behavior before we begin drawing. Calculating the maximum possible number of turning points allows us to place an upper bound on the visual complexity of any algebraic formula. A polynomial's overall shape is dictated by its highest exponent, a value known as the degree. This degree, denoted as n, shares a direct relationship with the number of roots the polynomial can have. As a baseline rule, a polynomial of degree n can cross the horizontal x-axis at most n times. To reach multiple roots, the curve must physically loop back toward the axis after each crossing. This looping motion is what creates a turning point. Therefore, the degree n establishes a mathematical ceiling for how many times a function is allowed to intersect the zero line. We can see this logic in action by starting with a degree 2 quadratic equation. If we plot two roots on the x-axis, we must use a continuous line to connect them. Reaching that second dot requires a single turn at the axis of symmetry. A degree 2 polynomial needs exactly one turn to hit two roots. This pattern extends as we move to a degree 3 cubic function. Here, we plot three distinct roots along the x-axis. Weaving an undulating curve through all 3 points requires two separate changes in direction. Geometrically, connecting n roots will always require n-1 turns. The n-1 rule is a strict geometric requirement for any continuous curve attempting to intersect the x-axis multiple times. We can verify this with a specific equation. F of x equals x minus 2 times x minus 4 times x plus 3. Expanding these three variable terms identifies this as a degree 3 polynomial. The roots are 2, 4, and -3. We map these to the plane. Drawing the polynomial curve through these coordinates reveals its path. We find exactly two turning points, one local maximum and one local minimum. The two observed turning points match our theoretical n-1 limit exactly. Because the roots are distinct and separate, the curve must travel across the axis and back, forcing the maximum number of turns to appear. The n-1 rule successfully predicts the visual complexity of these distinct root functions. A more complex case highlights a vital detail in the rule. The fifth-degree polynomial 1 plus x squared plus 4x to the fifth. For a degree 5 equation, n-1 gives us a limit of 4. Mathematically, this function is permitted to have up to 4 turning points. The actual graph of this function looks much simpler than a fifth-degree equation might suggest. If we count the turning points, we find only 2, a single peak and a single valley. There is a clear difference between the 4 turns we allowed and the 2 turns that actually exist. This is because n-1 is a ceiling, not a quota. A polynomial will have at most that many turns. While a graph may not reach its limit, it can never exceed it. A sketch showing more turns than the n-1 bound is mathematically incorrect. A final test case highlights a specific edge case, the equation f of x equals x minus 1 cubed times x plus 2. This is a degree 4 polynomial, meaning it has a maximum of 3 turning points. Plotting the full curve reveals a very specific geometric behavior. We can see one standard turning point at the bottom of the curve, where the function shifts from falling to rising. But at the coordinate x equals 1, the curve behaves differently, creating a visible shelf. At this point, the slope of the curve flattens to exactly 0. However, after hitting that 0 slope, the curve simply continues rising rather than turning back down. A curve that hits a 0 slope without changing its vertical direction creates a classification problem for our current geometric definition. Our algebraic definition of a turning point is binary. The function must change from increasing to decreasing, or vice versa. Because the curve goes from increasing to flat and then back to increasing, it does not meet the criteria for a turn. In the context of pre-calculus algebra, this flat spot remains unclassified. Basic algebra lacks the specific vocabulary to define the nature of a zero slope that does not result in a change of direction. To identify and categorize these points, we must move into calculus and utilize the derivative. Algebra provides the essential boundaries for the polynomial curve, but calculus is required to map its true anatomy.